In this video, we will explore page table used in the paging system. Page table is kept in the main memory. Each process has a page table. Now, there are two registers to support the page table. One is a page table base register. This register points to the base address of the page table. And the page table length register, it indicates the size of the page table. The operating system will create a page table for each process. The page table entries store the frame numbers. Now, every data instruction access requires two memory access. One memory access is for the page table to get the frame number from the page table entry. Another memory access is to get the data or the instruction from the main memory. We know the memory access is much slower compared with the processor or the CPU speed. The two memory access problem can be solved by using a special fast lookup hardware cache called translation look asset buffers, TLB. This works as a cache between the main memory and the registers. TLB is a fast speed cache. So the access speed to the TLB is close to the register access. And in the TLB, each entry of TLB consists of two parts, the key and a value. Search a key from TLB is very fast. So the key is a page number. So page number are stored as a key in the TLB. And the frame number is stored as a value corresponding to the key. So for example, the page 5 is stored in the frame 100. And the page 11 is stored in the frame 201. Okay, now we store the page number and the frame number pairs in the TLB. The TLB capacity is typically small. So that means the TLB is not enough to store the entire page table, to store all the page table entries. So TLB only contains a few of page table entries. Now the CPU generates a logical address. We know the logical address has two parts, page number and page offset. The memory management unit checks if this page number P is in the TLB. So if this page number is in the TLB, we say we have a TLB hit. The MMU will get the corresponding frame number F from this TLB. So in the TLB, search the page number. Page number is a key. Search the key page number from TLB. If the page number is in the TLB, get the corresponding frame number F from the TLB. And then combine the frame number and the page offset. Combine these two, get the physical address. Use this physical address to access the memory unit. If the page number is not in the TLB, here we have the TLB miss. Now the CPU need to access the page table in the main memory and get the frame number from the page table. And then add the page number and frame number into the TLB for fast access next time. So add this pair. The P is a key and the frame number is a corresponding value. Add this pair in the TLB. And then access after get the frame number from the page table, combine the frame number and the page offset to access the main memory. Now this figure shows how the TLB works. The CPU generates a logical address. The logical address is divided into two parts. P is a page number. D is a page offset. So first, CPU check if this page number is in the TLB. The TLB contains some entries of the page table. Now this page number and the corresponding frame number. TLB does not contain the entire page table. Okay, if the page number is in the TLB, we have a TLB hit, and then the CPU will extract the frame number, from TLB and combine the frame number with the page offset, get the physical address. Okay. If the page number is not in the TLB and there is a TLB miss, and then the CPU accesses the page table in the main memory. Now the page number is used as an index for this page table. Extract the frame number from this page table entry, and then combine the frame number and page offset, get the physical address to access the physical memory. This is how the TLB works. Now let's analyze the effective access time. Now the TLB hit ratio is a percentage of time that a page number is found in the TLB. The 80% hit ratio means that we can find the desired page number in the TLB 80% of time. Now suppose that it takes 10 nanoseconds to access main memory. So if we have the TLB hit and the page number is in the TLB, so that means we only need one memory access. One memory access to get the data or the instruction, it's a 10 nanosecond. If we have the TLB miss, we need two memory access. One for the page table and one for the data or the instruction. So it takes 20 nanoseconds. So the TLB hit, we need the 10 nanosecond access the memory once. If we have a TLB miss, so we need two memory access to access page table and access the data or instruction. It takes 20 nanoseconds. The effective access time can be calculated as this. 80% of time we need one memory access. And 20% of time we need two memory access, 20 nanoseconds. So the effective access time is a 12 nanosecond. Now, 12 nanosecond means a 20% slowdown in the access time. Now, if we had the more realistic hit ratio of 99%, if the hit ratio is 99%, the effective access time is a 99% times 10, one memory access, and plus 1% time we need the two memory access, 20 nanosecond. So the effective access time is a 10.1 nanosecond. This means 1% slowdown in the access time. So we can see the TLB can efficiently solve the two memory access problem. The memory protection in paging. In the paging, memory protection can be implemented by associating protection bits with each frame to indicate if this frame is read-only, if the read-write access is allowed, or if this page or if this process is executable. Here we can attach the valid and invalid bit to each entry in the page table to show if this page is valid or not. If this bit is valid, it indicates that this associated page is in the process logical address space. So this is a legal page. Invalid indicates that the page is not in the process logical address space. This is an illegal page. If a process tries to access an illegal page, it will cause a trap to the operating system. In this example, this is a logical address space. The logical address space has 6 pages. Has 6 pages from page 0 to page 5. And now in this page table, the page 6 and page 7 are invalid. And the page 0 to page 5 are valid. So this means page 6 and page 7 are not valid page or are not legal page for this process. So these 2 pages are invalid. If a process tries to access the entry 6 or the entry 7 in the page table, it will cause a trap to operating system. And now the structure of page table. Now the memory structure of paging can get huge using straightforward method. Now consider we have a logical address space. The logical address has 32 bits. So the logical address has 32 bits. That means 32 bits, m equal to 32. Okay, now that means the size of logical address space is 2 to the 32. 2 to 32 bytes. The size of logical address space is 2 to 32 bytes. Now assuming the page size is 4 kilobyte. So 4 kilobyte is equal to 2 to 12. Now n equal to 12. The page offset has 12 bits. The logical address has 32 bits and the page offset has 12 bits. So that means the page number has 32 minus 12 has 20 bits. The page number has 20 bits. That means the page table has 20 bits, or there are 1 million entries in the page table. 1 million entries in the page table. If each entry is 4 bytes, and now each process need 1 million times 4 need 4 megabytes just for the page table. Okay, each process need 4 megabytes of physical space just for the page table. But it's not easy to allocate contiguous 4 megabytes in the main memory. Now, if we always require the contiguous memory space, so we have the external fragmentation. One simple solution is to divide the page table into smaller units. So here we have the hierarchical paging, hashed page table, inverted page table. And now we will talk about the hierarchical paging. Hierarchical paging means that we can have the multiple level page table. Now this is an example of two-level page table. Two-level page table means we divide the page table into multiple pages. We page the page table. Okay, now assuming this is a page table, and this page table is too big, so we divide this page table into the smaller partitions. We divide this page table into pages. So we break up the logical address space into multiple pages. And we break up the page table into multiple pages. And then we create an outer page table. The entry of the outer page table points to the address of each inner page table. Okay. So we call this outer. This is the outer page table. This is the inner page table. The entries in the inner page table shows store the frame number for the physical memory. For the outer page table, this entries shows the base address of inner page table. Now for the two-level paging, now assuming we have a logical address, the logical address has a 32 bits, and the page size is a 4 kilobytes. The page size is 4 kilobytes, means the page offset has 12 bits, because a 4 kilobyte is equal to 2 to 12 bytes. So the n equal to 12. The page offset has 12 bits. Now the page number has m minus n bits, m equal to 32, and n equal to 12. M minus n equal to 20. So the page number has 20 bits. Now we page the page table. The page table, okay. Now the page table is paged. The page number is further divided into two parts. So we have the 10-bit page number and 10-bit page offset. Okay. Now in this example, these 12 bits, the low order 12 bits are the page offset. And these 20 bits are the page number. But we continue to split this page number into two parts. And the P1, 10 bits, is the index for the outer page table. And the P2, 10 bits, can be used as index for the inner page table. Now, here, this is the two-level page table. And we divide the logical address into two parts. Page number and then page offset. And then we continue to divide the page number into two parts. P1 is used as the index for the outer page table. Get the address of the inner page table. And now the P2 is used as an index for the inner page table to get the entry from the inner page table. And in this page table entry, we have the frame number. and combine the frame number with the page offset, we get the physical address. This all about the page table. This video will stop here.